expressions. And simplifying trig expressions is the next thing that we want to start to do with these identities. Okay, now I'm going to give you a trig expression here in a second, and I'm actually going to sort of challenge you and say, why don't you see if you can simplify it, even though you might be saying, but I don't know what that means. Okay, but I'm kind of purposely giving you a problem, and I'm trying to set you up a little bit here for success. Like this trig expression, let me just show it to you, and so you can copy down whatever you want to copy down. It says tangent times cosecant. So that's a trig expression. Tangent times cosecant. It turns out that it can be simplified. It can actually become something simpler. Something simpler. So how? Okay, well, I want you to kind of play with this a little bit, but it's kind of neat. If you just try, you could change tangent. That's kind of my little hint. You could change tangent. And you say, what do you mean change it? Well, if you look in your little identity book, there's something that you might be able to say the tangent equals. Now, it's the same thing with cosecant. You could change it. Okay, now, if you try and you change tangent and you change cosecant, you just might find out that it can be simplified. Again, it can turn into something simpler. Okay, this is kind of one of those times where I purposely am not showing you something, but I'm hoping that you're willing to try. And you never know. You might surprise yourself. Now, just as kind of another hint, as you look in your book, if you're using that little book we wrote the other day, you don't have to look too far. You, in fact, only have to open it up to the first page. But you do not need to go into the Pythagoreans, and you don't need to go anywhere beyond just the first page or the first 2 pages, if you want to call it that. How can you change tangent? How can you change cosecant? And if you change them, do you see how they can simplify? Now, I still want to give you guys a chance to try to do it, but it sometimes helps to just hear from a classmate, and maybe something will sort of a light bulb will go off. So, Cassidy, just how did you change tangent? Good. And if you don't mind, we're just going to cut you off right there, but that is exactly right. You can change tangent to be sine x over cosine x. Now, some of you are saying, but I changed a different way. It's all right. You kind of sometimes you just learn by trying, but you can change tangent to sine over cosine. And Nick, can you just tell us how you change cosecant?
I did the research, but that doesn't follow the same pattern.
But it's okay. So go ahead. How did you change it? 1 over?
Sine.
Good. Now, it's all right. You even kind of said, but it doesn't follow the same pattern. Well, you'll find out that changing it that way allows you to simplify. And again, try to pick up where these students took us. If you're saying, well, what am I supposed to do? See if something simplifies, and then see if you can continue to write your answer using the identities. You're close. It's just the position of your answer. Numerator versus denominator. All right, so Justin, what you had sort of as your next step looks perfect. I'm just curious, can you verbalize it? What would you do for your next step?
So I put it together since the two sums is together.
Now, it's important that he said he multiplied them together. That is exactly right. You do the multiplication. But when you do the multiplication, rules of fractions would say that these cancel. Now, everyone out in the crowd, look at that 1 over cosine. And can you change it? Can you write it as something simpler? Since it's 1 over cosine. Well, you could change it to, good. Okay, and that represents our simplified version of tangent times cosecant. All right, now we opened up a can here. It's actually a pretty big can, but when you open up the can, you realize that you can take your identities and you can use them to change your expression. And then as you change it, it starts to simplify. And of course, we end up with an equivalent answer. Let's step back a second. Okay, what does it mean to simplify something? Well, what we just showed you is an example of taking what you start with and writing it as a single trig function. So if you're able to write a single trig function, definitely it's simplified. Okay, now it's not always going to work out that you end up with just a single trig function like secant for this one. It might be that you're able to take your given and write it as a numeric value. A numeric value, like a number. That will be simplified. And you guys will find out through today's lesson in the next couple days that sometimes, because exponents are in use, that you end up with just a lower exponent. You end up with a smaller exponent. And that will be simplified. Okay, now, you can't kind of put this in a nice, neat box, although I'm trying to a little bit by giving you guys some suggestions on what it means to be simplified. But it's also true, if you can read that vertically there, that it could be any combination of these things. And we're not kind of ruling out some other possibility. And you'll get the idea as we obviously start doing this, but I just want to get you a starting point that this is what we mean by trying to end up with something that is simplified. Now, what I've done is really carefully created a lesson that's going to have some examples that kind of keep showing us more ideas. Those ideas we will highlight when we're done with the example. What I'm really trying to do, though, is give you guys tools that you can then use for like another example, basically a new problem. And so every problem that we see today is kind of intentionally trying to show us something new. And I want you to understand that I'm trying to get you guys eventually to a point where obviously you can do this on your own. Okay, but let's kind of go a step at a time here. So here's another expression, tangent cosecant over secant. Tangent times cosecant over secant. Now, I actually would like to just kind of give a suggestion here because there's really like I don't want to call it a shortcut, but it is a good way to interpret both of these reciprocals. Do you see the reciprocals? Let me just show this because I want to give you guys like a method on how to deal with this. I've seen students make this too complicated. Now, each of these is a reciprocal, okay? But I'm going to skip writing them as 1 over. The reason I'm going to skip writing them as 1 over is because I can accomplish that concept by flipping each of these. Okay, now I want you to know that these arrows I'm drawing insinuate the idea of doing the reciprocal. Okay, but I'm not showing that reciprocal as a 1 over. Okay, instead, I'm going to show the result. Now, the result of flipping secant is doing its reciprocal. But when you do the reciprocal of secant, you get a new function. You get the cosine function. Now, it's going to be the same thing with this cosecant. Okay, I'm doing its reciprocal by flipping it, but I get a new function. I get the sine function. We'll keep doing that. Okay, but what I did right there was very similar to what you saw here, where we changed cosecant to be 1 over sine. I just skipped writing the 1 over, okay, because I already had a fraction that I could flip. Tangent. Just like you changed it over here to be sine over cosine. We're going to make the same change. We're going to change tangent to be sine over cosine. But I also want to show you how I can take that tangent and kind of take it out of the numerator, because it's just a multiplication problem anyway. This multiplication sign right here, whether it's in the numerator or whether I kind of separate it, is still going to become, is still going to be a multiplication problem. And so I've shown you a way that I can reinterpret tangent as sine over cosine, and that's legal.
Could you just look tan and cosecant in the numerator and cosecant?
Yeah, you actually could have just done maybe one of these flips. I've seen people say that they don't want sine to come down here. Okay, and that there would be a way that we could end up with our final answer. That is definitely true. I went this route because I wanted to show one more time how when you have sines and cosines, when everything's sines and cosines, they often can interact with each other. And this was a really nice interaction because crossing them off insinuates that they all divide to be 1. They all divide to be 1. And again, Hannah, and really everybody, soon you're going to realize that there's many ways to go about these problems. I'm obviously showing one way, but there's often many ways to go about them. I'm also going to be delivering you guys like what I call little nuggets of advice. And those nuggets of advice kind of go with the problems. You can put them off to the side. You can make a little box somewhere. I think we're going to have like 6 nuggets here, so how much space you might need. But something that's happened now in 2 problems is that we basically have turned everything into sine and cosine. That is probably the most common strategy, changing everything to sines and cosines. Okay, because sines and cosines often can interact, okay, meaning they might cancel. You might be able to put them together. All right, now, I don't want to stand up here and make it sound like you always do that. I'm just saying that that's a really common strategy. There's really not going to be an always for anything today, because you'll find out that these problems we're working on really require some critical thinking. And critical thinking isn't something that we can put in a nice little box and say, you just do this and then you do this. Instead, you have to think. So here's another expression, which purposely is going to require some different thinking. It's sine squared plus sine squared tangent squared. Sine squared plus sine squared tangent squared. Back in algebra class, it could be that the teacher said, but if they didn't, I'm going to kind of remind you right now that when you have a function, when you have a term, when you have some type of expression that repeats itself. Okay, now I underline that sine squared because it's repeating itself. Often you can factor things that are repeated. Now, the type of factoring that I'm talking about here would be like a GCF factoring, where, you like take out the sine squared. Now, when I say take out the sine squared, that also implies that I divided it out. So when I divide sine squared off of this sine squared, well, I'm left with still the number 1, not 0. Okay, because again, we're dividing it out. Now, when I take sine squared off of sine squared tangent squared, you're still left with the tangent squared. Nothing changes there. So here's a good example of factoring. It's also a good example of an identity. Okay, now what I just highlighted there, 1 plus tangent squared, as you guys get better at this, you'll kind of recognize it. Right now, you may be looking in your book. Now, when you look in your book, I hope you're looking at some squares, like the center page, the Pythagorean page. Do you see 1 plus tangent squared? I just want you to look for it. I don't expect you to have it memorized, but you should see that 1 plus tangent squared is equal to secant squared. Secant squared. Okay. Now, that's a Pythagorean identity. Why would we want to do that? Okay, a lot of the reason why behind a lot of these problems is because of what comes next, because of how you can simplify. So secant squared is the same as 1 over cosine squared. But again, why would I want to do that? Why would I change secant squared to 1 over cosine squared? Well, because again, of kind of what comes next when you simplify. Now we get to a point here where we want to realize that we've got 2 fractions and they want to be multiplied together. Okay, it's when you multiply, remember that you just multiply across the top and bottom, not cross multiply, but just across. You multiply across the top. Basically, you get sine squared over cosine squared. Those ones, obviously, nothing changes there, but sine squared over cosine squared, now that is equal to tangent squared. And now we are simplified. Basically, we're simplified because there's nothing more that we can change. And we, of course, have one trig function. Okay, that's a good problem. That actually had 2 nuggets of advice that I want to throw into this one. The first one was definitely the idea of factoring. Okay, honestly, if you didn't factor this one, we'd have a tough time coming up with some type of new answer because we had a repeated function factor. There's something else that slid into this problem that will become another big idea. Okay, anytime you have squares, think Pythagorean. Now, I'm not saying that that's a guarantee, but again, it's a good piece of advice. If you have squares, think Pythagorean. Now, sometimes students get like a little Pythagorean happy, like everything they want to be a Pythagorean. If you go back to the first problem, and quite frankly, any problem that didn't have squares, sometimes I see kids doing this, like just inserting a square, maybe like squaring both sides. The problem with that is that this isn't both sides. We don't have like an equation. And so if I just kind of like put a square in here, what I've really done is I've changed the value of the problem. It's no longer tangent cosecant. It's like a whole different problem. Listen, the moral of the story is you can't like just put squares in, okay? They have to be sort of given to you. In fact, for all these problems, you can't just put something in. It's what you're given, okay? And you take what you're given and you try to simplify it. So let's take this 1 plus cosecant over secant minus cotangent. So we're going to take what we're given and simplify. As you copy this down, this problem is intended to start getting us talking about fractions. Many of you, well, some of you commented on the little preview activity. You said that I need help with fractions. I like that you are aware, and that's why I'm mixing these problems in, because we need to talk about fractions. This particular fraction, if you look at the numerator, it's separated into terms. Terms are things that are split with plus or minus signs. Okay, now it's also being divided by a single term in the denominator. If all that stuff is happening, namely that you have a single term in the denominator, then you're allowed to, and I'll even say that you probably should, do like a heart method, where you basically split the denominator equally to both parts of the numerator. Okay, so what's happening here is I'm taking the secant and I'm applying it to the entire numerator. Some people call it the heart method. What does that do for us? Some people think that it makes the problem look worse. Okay, sometimes you just have to be willing to try something now and see what happens. Okay, now one thing that I see here is that everything that's on the board is really a sine or cosine in disguise. Okay, let's go that route. Everything's a sine or cosine in disguise. 1 over secant is really just cosine in disguise. Now, here's another opportunity for us to consider Mr. Naylor's sort of little reciprocal trick. It's 100% legal. I can skip writing this as 1 over this or 1 over that, and I can just move secant up to the top. But when I move it up to the top, I'm doing its reciprocal, so it really changes into cosine, and then I can move the same thing, the numerator down to the bottom, but it changes into sine. Everything is a sine or cosine in disguise. Okay, cotangent is a sine or cosine in disguise. It's actually cosine over sine. Now, there would be some things that we could have done differently here, but in the end, we arrive at the same place. We arrive at two fractions that actually just cancel each other. They basically subtract and wipe out to be 0. Okay, so if that happens, then let's take full advantage of that. Obviously, you're subtracting two fractions that are exactly the same. So I still have cosine, and cosine plus 0 is just simply cosine. Okay. One of the reasons that we did that problem is so we could highlight some stuff about fractions. Okay, let's talk about fractions a little bit. Sometimes a fraction just gets simplified. Now, if you're going to write that down, make sure you know what I'm referring to. That's what kind of happened in the first couple problems. When we canceled the signs, I just call that simplifying. In this problem, we canceled everything. So sometimes fractions can simplify. Heart method. Heart method was more specifically this problem. Okay, remember, if you're going to do a heart method, you have to take the denominator and apply it to the entire numerator. You have to split it. And then we have the common denominator. I know a little phrase that you guys are familiar with. You even practiced it a little bit in the preview activity. Okay, let's do a common denominator problem that uses sines and cosines. Okay, so I'm already telling you that this problem is going to make us think about common denominators, but let's approach it and make sure we see why. So I've got secant times cosecant minus tangent. Secant times cosecant minus tangent. By the way, you see a little bit why I was trying to give a little sales pitch for the homework. These are the kind of problems you're going to be doing. I want to really encourage you that when you sit down and do this homework, that you have you're in a good mood. You're ready to do some math. You have some time. These are going to be problems that you have to think a little bit about. They're not just going to be punch out some answers doing the same steps over and over. Okay, some of those homework problems you might not get correct. Don't use that as an excuse, though. Try them. Okay, especially the ones near the end of the assignment. Okay, they're a little more challenging, but try them. It's going to be the next step in you guys' process of learning this. Okay, now listen. If this problem is just kind of front and center, and you had no idea what you were going to do, I could completely understand that you might not think common denominator. I mean, there's not a fraction on the board. It's not even a fraction. So how do you know that it's going to be a common denominator? Well, I don't think you know until you start to make some changes. Like I hope you change secant to be 1 over cosine. I hope you change cosecant to be 1 over sine. Okay, now we're kind of using, as I said, that strategy where you change things to sines and cosines. You don't do that all the time, but sometimes, if there's nothing else that you can do, you should change and see what you have. Now we have fractions. Okay, and these fractions are being multiplied, so I would suggest that if you didn't do so already, that you just write that as just one nice 1 over cosine sine. 1 over cosine sine. Okay, and then we have this sine over cosine. All right, so this is a perfect example of common denominators, okay, because there's no way you can add or subtract fractions unless the denominators are the same. Now, this denominator has a cosine and a sine. This denominator has just a cosine. That means that this denominator needs a little more. It needs a sine. Now, I hope you wouldn't think that you can just put sine down there without also putting it in the numerator. In other words, remember how to make a common denominator? The teacher should have said that you multiply the top and bottom by the same thing. In this case, the thing is sine. Okay, now when I multiply top and bottom by sine, I now have a common denominator. I like to sometimes just write that common denominator, which allows me to take the numerators, 1 minus sine times sine. Now, we should be changing sine times sine to be sine squared. But what I'm getting at is that now you can actually do the subtraction. Now you can actually take 1 minus sine squared. And again, I wrote it over the common denominator. Okay, maybe you would, in all honesty, you would say, man, I don't know if I would have figured that out. I get it. Like, I'm not sure if I expect you to figure this out. That's why I'm showing you some stuff. But next time you see a problem like this, you'll be thinking about what happened here. And look what happened here. We created a sine squared. Okay, now we created a sine squared legally. And when you have a 1 minus sine squared, it's not going to take you too long to realize that 1 minus sine squared is equal to an identity. Okay, and it's okay to look at it right now. Look at it in your notes, look at it in your book, because 1 minus sine squared is cosine squared. You'll get pretty familiar with that. Okay, so we're getting warmer because we're getting to a point that we can simplify this. We can simplify this. Now, there's a cosine in the bottom that cancels with one of the cosines in the top. It's okay if I cross off that square so that I can get cosine over sine. And I hope you wouldn't leave it as cosine over sine. Since you're able to change that to be cotangent, you should. That's a good problem. That's a good problem. If you take a look at where we started and where we finished. Okay, common denominator. I've carefully designed 2 problems for you to try. Okay, the reason I say carefully is because they have just a little bit of new tactics mixed a little bit with some tactics that you've seen that should allow you to try these. Okay, see if you can simplify these. tell you what, you guys have come a long way. Keep working on it, but you've come a long way in 30 minutes. One thing I'll share about the first one. Be careful. Some of you were a little quick to cancel the cosine squareds. Now, you're allowed to cancel the cosine squareds, but you have to also, do you know what I'm going to say? You have to also take that cosine squared over here. Okay, cosine squared has to go to both, for those of you that were thinking that way. Now, there's another way to do the problem altogether. But to my friends that did this, make sure you also take it over here. Take it over here. It's a heart method. If you're a little thrown off by the second one, think FOIL. Think FOIL. Just do the algebra. Thank you. These before time expires. So a lot of you did this, and that's correct. It actually comes out to be 1. But what happens when you do this? What happens when you actually apply it to the other side? Okay, you get something, right? You can show it if you need to. Some of you might feel like you're ready to skip some steps already. So you can show it, or you can change it right away to be tangent squared plus 1. Okay, even though it's kind of the first day that we've really been doing this, tangent squared plus 1 will start to look familiar to you. You'll say that that is equal to secant squared. But there's another way, isn't there? How did you do it? How did you do it? Okay, go ahead, Hannah.
I think sine squared plus cosine squared is 1.
Okay. I assume you just left cosine squared in the denominator.
Yeah. And then I just leave it as cosine squared.
Okay. Now listen, we're not standing up here and saying that one way is better than the other. This is actually more of what's coming, that you guys, as long as you do it the right way, as long as you do good algebra, you should arrive at the right answer. Okay, so both these are great. Maybe you showed all that. Maybe you right away kind of canceled some of those signs. But eventually, the FOIL method would produce 1 minus sine squared. Another will become a familiar phrase to you guys. 1 minus sine squared is the same as cosine squared. All right, now page 3, 4, 5, and page 3, 4, 6. It goes on to the next page, but really important homework assignment. Okay? So we'll see you back here tomorrow. The chalkboard will be divided up. Okay, many of these homework problems we're gonna get up there tomorrow.